Okay, good morning. The last lecture, that is the fourth video lecture, we have seen about the operations on the dependent and independent variable. Now we will see the classification of systems. Classification of systems. So systems are classified into linear and non-linear, time variant and time invariant, linear time variant and linear time invariant, static and dynamic, causal and non-causal, invertible and non-invertible, and finally the static and stable and unstable system. So these are all the basic classification of the system. In the universe, all the systems comes under any one of these or more than one of these categories. For example, if you take linear time invariant system, so in linear time invariant system, it is having linearity principle and time invariant. So the system which comes under this category will also comes under first two categories. Like that, all the systems in the universe can come any one or more than one of these categories. So coming to the first one, linear time variant. So we will see. So as we know that a system is combination of, or it's a block which can take inputs and produces some output. Here x of t is the input and y of t is the output, where t is the transform tool that is used to transform the input, that is used to transform the input and produces output. So y of t can be related as transformation of input. Y of t can be related as transformation of input. So this is general notation of any system. Let us take the first system. Let us take the first category, linear and non-linear system. System is said to be linear if it satisfies the principle of homogeneity and superposition. What is meant by homogeneity? If a system takes input x1 and produces output y1, then if you give a scaled input, that is a x1, the system has to produce scaled output a y1, that is called homogeneity. Superposition, if you give multiple inputs, then it has to put the multiple output. For example, x1 produces output for a system, x1 produces for a system due to x1, y1 is the output, due to x2, y2 is the output. If you give combined inputs, that is x1 plus x2 to the same system, it has to produce output, it will be of the form y1 plus y2. That is, sum of the inputs should produce individual sum of outputs. So that is called superposition. So any system that satisfies both superposition and homogeneity principle, that comes under linear system. So this is the necessary condition for the homogeneous linear systems. For example, that is transform of a1 x1 of t plus a2 x2 t. That is, here we are taking the scaling homogeneity and summing the scaled or weighted sum of inputs. That is, it is having both homogeneity as well as superposition, and the output should be weighted sum of output. For example, in this, therefore the transformation t of a1 x1 of t plus a2 x2 of t is equal to transformation of a1 a x1 of t plus transformation x2 of t y1 of t plus y2 of t. So a y1 of t plus a2 y2 of t. So weighted sum of input are producing weighted sum of output. So it is satisfying both superposition and homogeneity, and the system is linear. So this can be explained easily by using this example. So it is an example for non-linear but not the linear, because linear we have defined, we have in the non-linear example. For example, if the system is x of t is equal to x square of t. So if you change the input x1, then the output is y1. So y1 of t is equal to transformation of x1 of t, which is equal to x1. Instead of x of t, we are giving x1 of t as input. So x1 square of t. Similarly, For x2 of t, the output is y2 of t. So y2 of t is equal to transformation of x2 of t is equal to x2 square of t. So transformation of a x1 of t plus a2 x2 of t. Scaled weighted sum of inputs. Outputs is transformation of x1 in where x1 plus we are having a x1 plus a2 x2 whole square. So whole square it is a plus b whole square. On expansion this formula, the resultant value is a1 y1 of t plus a2 y2 of t plus 2 a1 a2 x1 square x1 of t x2 of t transformation like that. So the weighted sum of input is not equal to weighted sum of output. So then the system is non-linear. So like that you can check the linearity conditions for the given problems. Similarly, the next one is time variant and time invariant. A system is said to be time invariant if its input and output characteristics does not vary with time. So, for example, if you apply an input change, the output change must be exist. Such systems are known as time invariant system. If this condition is not satisfied, it becomes time variant. For example, take this simple example. For example, if y of n is equal to x of minus n, then y n comma t means transformation of x of n minus t have delayed by, okay, they will change the input by minus t units. So x of n minus t, that means x of minus n minus t. So this is the output delayed, output change. Okay. If you define the output change y of n minus t means x of y of n minus t, that is x of minus n. So minus of n minus t minus of n plus t. So both are not equal. So that system is time variant. If they becomes equal, the system becomes time invariant. Like that, the one can check the time variant and time invariant systems also. Linear time invariant. If any system is linear and time variant, that is called linear time variant. If the system is linear and time invariant, the system is linear time invariant. Next one is static and dynamic system. The system with memory is static system. The system without memory is static system. The system with memory is dynamic system. For example, y of t is equal to 2 into x of t. Y of 0 is equal to 2 into x of 0. Similarly, y of 1 is equal to 2 into x of 1. At any time, the output is depends upon present input. So it does not require any memory. That is static system. For example, second example, y of t is equal to 2 into x of t plus 3 into x of t minus 3. Y of 0 is equal to 2 into x of 0 plus 3 into x of minus 3. Present output y of 0 is depends upon present input x of 0 and past inputs x of minus 3. So to evaluate current output, it must memorize the previous inputs also. So it requires some memory. Such systems are known as dynamic systems. Causal and non-causal system. If a system is said to be causal if its present output depends upon present and past inputs only, but it does not depend on future inputs. Such systems are known as causal systems. If present output depends present and past and future inputs, then it is called non-causal system. For example, y of n is equal to 2 into x of t plus 3 into x of t minus 3. Present output y of 0 is equal to 2x of 0 plus 3x of minus 3. That means present output depends on present and past inputs only. The system is causal system. In this case, present output depends on, for suppose y of 0 is equal to 2 into x of 0 plus 3 into x of minus 3 plus 6 into x of 3. That is, present output depends upon present, past and future values of the input. Then the system is non-causal system. then the system is non-causal system. Next, invertible and non-invertible system. If the output is equal to the input, then the system is said to be invertible system. Usually this type of system will not be exist, but in some situation it requires to design the output and input exactly similar. For example, if the system is there, H1 is the transfer function, H2 we have to design such that the output y of t should be resemble to the input, then H2 of t is said to be invertible system. If this condition is not satisfied, that is non-invertible system. Stable and unstable system. For bounded input, if the output is bounded, then the system is stable. If that is also called BIBO system, BIBO system. If bounded system produces unbounded output, that is unstable system. For example, y of t is equal to x square of t. So here input x of t is bounded, output y of t also bounded output. So the system is stable. Suppose if it is y of t is equal to integral of x of t, there are no limits. So the system is unstable. So this is about the classification of systems. Next we will see the convolution and correlation, which is a very important formula of a tool to calculate the convolution output of systems and correlation, the relation of the characteristics signals. First one, convolution. Convolution size, it is usually known as convolution size. Convolution is a mathematical formula that is used to estimate the output of an LTI system. LTI means linear time invariant system. So y of t is equal to x of t convolution with h of t, where x of t, y of t is output of LTI system and x of t is input of LTI system, h of t is impulse response of the system. Impulse response, when the input is impulse, the output of system is known as impulse response. That will be discussed in the 4th unit very clearly. There are two types of convolution based on the independent variable t: discrete continuous convolution and discrete convolution. Continuous convolution is defined as the system is continuous system. Input is x of t, output is y of t, and system response transfer function is h of t. So y of t is equal to transformation of x of t. The transformation is indicated by using this convolution sum. Y of t is equal to x of t convoluting with h of t. So the convolution sum is formula is integral minus infinity to plus infinity x of tau h of t minus tau. This can be written as minus infinity to plus infinity x of t minus tau into h of tau d tau, that is equal to h of t into x of tau. So this is known as convolution. The output is convolution sum of input and the system response h of t transfer function. So this is where the system is continuous, so it is continuous convolution. And for discrete convolution, the system must be a discrete one. Input is x of n, output is y of n, system response is h of n. So y of n is equal to x of n convoluting with h of n. So y of n is equal to x of n convolution with h of n. Sigma k tends to minus infinity to plus x of k into h of n minus k. Sigma k tends to minus infinity to plus infinity x of n minus k into h of k, h of n into x of n. So this is the convolution sum in the discrete functions. So this is about the convolution of the system. In the next session we will see about the correlation, definition, and the analogy between signals and vectors. Thank you.